Good day, Math 107 students, and welcome to the class activity for Lesson 4, which is linear and rational equations. So let's take a look at solving this first rational equation. And remember, what makes this different than a regular old linear equation is that we have a variable in the denominator. So both of the denominators are already factored, and 2x is already a multiple of x, which is nice. So we know our lowest common multiple will just be simply 2x. And if you forgot about how to find that, you take your first denominator and you make a little circle with the factorization inside. And since there's only one factor of x, you put the x inside. And then we make a second circle for our second denominator. And our second denominator is 2 times x. So we're going to intersect our circles and scoot on in there and borrow that x and then put the 2 right beside it. So the LCM is formed by simply multiplying straight across my circles, and I get 2x for my LCM. Well, both of these denominators would be 0 if x equaled 0. So that's going to be my excluded value. So now I'm all set to multiply each and everything on both sides of my equation, multiply both sides of my equation by 2x. So all I do is I write each of my pieces of my equation, and I just extend that fraction bar a little, make it a little bit longer in each case, so I can multiply the numerator by 2x on every single piece of this equation, every part of it. Okay, I haven't broken any rules here because what I've done to one side of my equation, I've done to the other. Okay, so remember, we're not creating common denominators of 2x. We're using 2x to multiply both sides of this equation so we can get rid of those denominators and have a nice, easy linear equation to solve without any fractions. So let's reduce this. X divides into x, and we get 1 there. So that leaves us with 4 times 2 on the left side, which is 8. And 2x divided by 2x gives me a nice big 1 again, and I get 5. And then I get 3 times 2x, which is 6x. So now it's time to solve this linear equation. And I subtract 5 from both sides, and I get 3 equals 6x. And now I divide both sides by 6, and I get x equals 3/6, which reduces to 1/2. Okay, so this is not one of my excluded values. So I'm very happy. And now all I have to do is just make sure I check my original equation, always the original, in case you made a mistake along the way. You wouldn't find it if you put your solution into one of the intermediate equations. You always want to go back to your original. So x is 1/2, so I'm going to put 1/2 in for x, replace each x with 1/2, and I see 4 divided by 1/2 is 8, because there are 8 halves in 4. And then this is 5. Well, 2 times 1/2 is 1, so that just gives me 5 plus 3. And I'm a happy camper because 8 equals 8. And therefore, my solution is 1/2. And as you know, your book, your author, always writes things as solution sets. So you use your curly braces and you put 1/2. It's okay for me if you just put the circle there. But if I asked you for the solution set, then this is what you would write. You would make sure you write your curly braces, which are the indication of a set, and then you would put your solution or solutions within that set. Okay, so we've got the first rational equation all solved. Let's take a look at the next one. Now this next rational equation, you have 2 different denominators on the left side, and I want to caution you here. I want to encourage you, not caution, but encourage you. Anytime you have a denominator that has an addition or a subtraction symbol, put it in parentheses, especially when it can't be factored. Like both of these denominators are already prime. They can't be factored any further. Now, This denominator on the second side, you'll notice on the right-hand side of this equation is both of these two denominators multiplied by each other. Now, sometimes they may start you off with an equation that looks like this. I just want to show you what the previous step may have looked like. It may have looked like this. See? And this is not factored. So you would have to factor it to be x plus 2, x minus 2. This factoring is should be a recognizable form for you, that this is the difference between two perfect squares. So you can factor it very quickly. The square root of x squared is x, the square root of 4 is 2, and then you put a plus and minus in your each, a plus in one factor and a minus in the other. These are actually called conjugates, these factors, but you'll learn that a little bit later. All right, so if it started off looking like this, you'd have to factor it, and then you would get this form. So notice what values in the denominator will make each denominator 0. Well, this denominator will be 0 if x is negative 2, and this denominator would be 0 if x is positive 2. So those are your excluded values. Okay, so my LCM is already formed for us. It's the first denominator times the second denominator. Since both of these denominators are prime, if you did the little circle idea that I showed you earlier, here's your first denominator. Well, x minus 2, x plus 2 can't be factored anymore. And then you have your second denominator, x minus 2, and that's a completely different factor. So there's no borrowing here or sharing of factors. So you just multiply those two to get your LCM. So when both of your denominators are prime, you simply multiply them together. And notice if you look a little bit at your equation, you'll see it's already done for you on the right-hand side. So again, I'm going to multiply both sides of this equation by the quantity x plus 2 times x minus 2. And to do that, I take each one of my original parts of my equation and I just make my fraction bar a little bit longer because I'm going to multiply the numerator in every single piece of this equation by my LCM. Okay, so all I did was extend that fraction bar. It looks a little funny, I know, but now I'm going to write in the top. I'm going to multiply this first piece by x plus 2, x minus 2. I'm going to multiply this second term by exactly the same thing, x plus 2, x minus 2. And then the right-hand side by exactly the same quantity, x plus 2, x minus 2. In doing this, you find a common factor to the top and bottom, and you are left with 5 times x minus 2 as your first term. In the second term, you have the common factor of x minus 2 top and bottom, so you're left with 3 times x plus 2 as your second term. And then on the right-hand side, both x plus 2 and x minus 2 have a twin factor below, so you're just left with 12. So now you use your distributive property in each one of these terms, and you get 5x minus 10 plus 3x plus 6 equals 12. And now you combine like terms. You have 5x and 3x, that gives you 8x. And then you have negative 10 plus 6, that gives you a negative 4. And that all equals 12. Okay, from here, piece of cake, right? We add 4 to both sides, and we get 8x equals 16. And now we divide both sides by 8, and we get x equals 2. And we're proud of ourselves for getting all the way through this equation. And then you say, uh-oh, 2. Oh, yeah, if I put a 2 back here and try to check it, I'll get a 0 in the denominator. It's an excluded value. So what that means is, after all that work, there's absolutely no solution to this equation. What that means is you cannot find a value for x that would make the left side of that equation equal the right. So that means there's no solution. We have an empty set. We can't put anything in our solution set, and we can write that symbol for the empty set. Okay, so go through all this work. It's a little frustrating at the end when you come down and you realize that there's no solution. Well, it may not be frustrating. It's just part of the process. Okay, so that's two rational equations for you that should pretty much be able to prepare you for just about any of the homework exercises you will have in solving rational equations. Now let's take a look at an application of rational equations that deals with electronics. And even if you're not familiar with electronics or with this idea, you can still do the mathematics. So it says in electronics, the resistance of a circuit measures its opposition to an electric current. Resistance can be increased by adding resistors to the circuit. Resistors can be installed in series or in parallel. See diagram below. So if we wanted to measure the total resistance in a circuit for each of these types of installations, the installations that would be placing your resistors in series or the parallel installation, these would be the two formulas that we would use. So we're going to look at a couple of problems here, one where we're placing resistors in series and one where we're replacing them in parallel. And we're going to do the mathematics to solve for the total resistance. Okay, so two resistors are for the resistance in each resistor. That's a mouthful, isn't it? So let's take a look at the first problem. Two resistors are being installed in series. So right away, I totally just come up here and I say, okay, this is going to be the formula I'll use. It's a simple addition formula to get the total resistance. Okay, cool. So I know that before I even go any further, I can write R equals X plus Y. Okay. Now my second sentence, what information does my second sentence give me? It says the total resistance, so that's new information. The total resistance needs to be 100 ohms. Ohms is the unit that we measure resistance in. So the total resistance, you'll recall, is represented by the letter R, and that needs to be 100. So you can replace R with 100, and you're on your way. Not quite there yet. We need to know something about X and Y. We can't solve one equation that has two variables in it because it has an infinite number of solutions. For any X, you give me a Y that adds up to 100, and this can go on forever and ever. So some information has to be told to you that relates the number of ohms between these two resistors so that you could write X in terms of Y. So you just have one equation in terms of Y, or vice versa, Y in terms of X. Okay, so let's see what information of what the relationship is between the number of ohms in each of these resistors. That has to be told to us or we can't do this problem. So if we look ahead, it says the first resistor needs to have 45 more ohms than the second resistor. All right, or it needs to have a resistance 45 ohms greater than the second. So the ohms in my first resistor, and I just do this off on the side to help myself, is greater than the number of ohms in the first resistor is greater than the number of ohms in my second resistor. And this always helps me. So what I do is I decide that I have to decide which one of these to call X or Y, and it doesn't matter. However, since the number of ohms in the first resistor is being described by or in terms of the number of ohms in the second resistor, or since the number of ohms in the second resistor is the smaller number, that's what I always let my variable equal. Again, it could be X or Y, it doesn't matter. So let's just call that X. So I'm going to call X the number of ohms in my second resistor. And what do I know about the relationship between X and the number of ohms in the first resistor? This one's bigger than X. How much bigger is it? 45 more ohms. So that means X plus 45, and I put that in parentheses, is the number of ohms in the second resistor. So now I can complete this equation with just one variable by substituting X plus 45 for y. And now I have one equation with one unknown, and now I can solve for x. So I get 100 equals 2x plus 45. I subtract 45 from both sides, and I get 55 equals 2x. And I divide both sides by 2, and I get x is 22.5. So x is the number of, represents the number of ohms in my second resistor, which is 27.5 ohms. And my first resistor has to have more ohms. How many more ohms? 45. So 27.5 plus 45 gives me the number of ohms in my second resistor, which is 72.5. So that's how you would solve the first problem here in number 3 of the class activities. All right, so let's take a look at number B here. All right, so now two resistors are being placed in parallel. All right, so they're being placed in parallel, which means I want to use this formula. And this is a rational equation. Voila, this is the reason why it's in this particular section. So we're going to say now that 1 over r is equal to 1 over x plus 1 over y. Again, the total resistance needs to be 100 ohms. That's the value for R. So I'm going to replace R with 1 over 100. And the relationship between these two resistors has not changed at all. The first resistor needs to have a resistance 45 ohms greater than the second. So all the work we did in part A above, we can use again. So 1/100th equals 1 over x plus 1 over x plus 45. So now we have to multiply both sides by our LCM, which is 100 times x plus 45. It's all three of these denominators multiplied by each other. And that's because they do not share any common factors, so you simply multiply them together. They're all prime. Okay, so I take my first term on the left side and I make my fraction bar just a little bit longer, and I throw in 100x times x plus 45. And then I take the first term on my second side and I make that fraction bar a little bit longer, and I multiply the numerator by 100x times x plus 45. And then finally I have 1 over x plus 45, and I multiply that by 100x times x plus 45. All right, and now I do all my reducing to make this look a lot simpler. So in this first fraction here, I see 100 over 100, and I'm left with x times x plus 45 in the numerator and 1 in the denominator, which is great. That's what I wanted. Now in the first term on the right side of this, I have x over x. So I'm left with 100 times x plus 45. X over x gives me that 1, and I'm left with 100 times x plus 45. And then in my second term on the right-hand side, my x plus 45 cancels with my x plus 45 as the common factor top and bottom. So I'm left with 100x. Okay, whew, that was a lot of work already, and I'm not even done. So I distribute the x on the left-hand side of the equation, and I get x squared plus 45x. And on the right side, I distribute the 100 through, and I get 100x plus 4500 plus 100x. So now I combine like terms on the right side, and I get 200x plus 4500. And now to solve this equation, we have to put everything on the left-hand side or the right-hand side because we want to have this equal to 0. So I'm going to subtract 200x from both sides. And when I do that, I get x squared minus 155x equals 4,500. And now I subtract 4,500 from each side. And I get x squared minus 155x minus 4,500 equals 0. Now, just like if this was one of our denominators in our equation where we were trying to figure out what would make this 0, and this is why you studied factoring in the prerequisite chapter, we need to factor this expression on the left-hand side. So we're looking for factors of 4,500 that differ by 155. And those two factors, those two numbers that you multiply to get 4,500, is 180 times 25. And notice the difference between these two numbers equals 155. So those are the two numbers we use in order to factor this. X, 180, and 25. And since we ended up with negative 155x in the middle, the 180 carries the minus sign and the 25 carries the plus. So in order to solve this, you set each of these factors equal to 0. This first factor when it's 180, and the second factor when it's negative 25. Now we can have negative 25 ohms, so we call this an extraneous solution. So now we go back and we say, okay, x is 180. So if x is 180, then x plus 45 is 225. So my answer here is 180 ohms and 225 ohms. Okay, so 180 ohms, my first resistor, and 225 ohms in my second resistor. Okay. Now finally, this equation, this rational equation that solves for 1 over R, 1 over the total resistance, we could rewrite that so that it solved for R. That would be a lot nicer if we just had an equation that told us what the total resistance is instead of the reciprocal of it, 1 over R. So how would we go about solving this equation for R? Well, there's multiple ways of doing this. But if we're going to use the ideas of what we've just studied, then what we would like to do is we want to take this rational equation and multiply everything on both sides by the LCM. Well, we have an R, we have an X, and we have a Y. So RXY is the LCM. So I'm going to take each one of these pieces now and multiply each one of them by the LCM. RXY equals, I think you're familiar with this now, 1 over X times RXY plus 1 over Y times RXY. Here we go. Now, we know that we've created that multiple, so every one of these denominators will be one of the factors that appears in the multiple and will be able to be reduced. So we get XY on the left side, and we get RY for the first term on the right side, and then the Y's cancel here, and we get R X for my second term. So you say, okay, my goal is to solve this for R, and I don't have a single R here, but you could combine YRs and XRs. That would be X plus YRs, just as if this said 2R plus 3R, we add the 2 and 3 together. The only problem is we can't add Y and X, we don't know what they are. So this is a situation where you have two like terms here. You have YRs and XRs, so you have X plus YRs. Or another way to think about this, if this does not resonate with you, is to think about factoring R out. So it'd be R times X gives us RX, and R times Y gives us RY. Okay, so we want to solve for R, which means we want to get r all by itself with a 1 in front of it. So we divide both sides by x plus y. And we are done. X times y over x plus y is equal to the total resistance. Okay. So that takes care of a large part of the section with solving rational equations. And the last little part of the class activities here is again giving you some more practice with true-false questions. And again, I just want to mention to you that these true-false questions are at the end of almost every single section in your textbook. So if you're trying to give yourself some practice with true-false questions so you're familiar with this when it comes time for your quizzes and your exams, and also just to help you with thinking about things in a little different way as opposed to just applying some skills. It really deals more with some of the concepts, although some of these also deal with some of the skills. This would be a great way to give yourself that practice. Is every time you do a homework, turn to that part of your textbook, the last part of every section, you'll see examples called, do these examples make sense? And they give you some examples. And then usually after that, before the preview exercises, there's some true-false questions. And those would be great things to write into your homework notebook as well. All right, so let's take a look at this first one. If you reduce x squared minus 36 over x minus 6, do you get x plus 6? Well, we know that to reduce anything, we're looking for common factors. So since this numerator is a subtraction problem, we want to factor it, because we can't put a slash through anything unless it's completely factored. And the bottom is x minus 6. So now I see I have that common factor of 1, so my answer is x plus 6. So this is true. Okay. Now let's take a look at this one. 1 over x plus 2 equals 3 over x. This problem I've used quite a bit over the years, and it is one that just deals with your concept of how can we add things, what must be true. And if you just simply add 1 plus 2 and get your 3 and put it over x, then you're missing the idea that in order to add, things have got to look exactly the same. And if you notice, these two terms here do not have the same denominators. These are not like fractions. They're not like anything. So in order to add those, you have to change 2 over 1 to a fraction that has x in the denominator. And the only way you can do that is to multiply top and bottom of this number 2 by the same quantity, which is again a fancy form of 1. So those of you who have had 096 here, you're probably familiar with the term foo-foo. So 2x divided by x is the same as 2 over 1. So once you replace 2 over 1 with 2x over x, you now can add these, and you get that common denominator x, but you get 1 plus 2x. You do not get 3. So this is false. So how do you change the sentence so this is true? You could put a slash through the equal sign there, or you could rewrite this so you have the left side equal the right side, whichever way you want to do it. Okay. So that's the class activity for lesson 4. If you have any questions, let me know.